due dates in the announcement sections of the website. They're very important deadlines, and you need to pay attention to them because the course is closing up and there are certain deadlines that have to be observed. So, as I mentioned, today is artificial intelligence, and I'm going to talk in no particular order about a number of developing technologies in this field and how they relate to our study of human consciousness. The overlying thing is that we can learn from studying computer systems, and we can also design better computer systems by studying the human mind. And these two tasks have been going on hand in hand since about the 60s as we understand how information processing works. Remember, cognitive psychology is all about information processing. Well, so is computer science. So another note is be sure that you check out the slide notes for this chapter, which are different from the talk I'm about to give you. So the things that you're going to see in the talk today are just to kind of illustrate the concepts that they talk about in the book, but it's going to be way out of order and totally random. So remember, you're going to be tested mostly on the book, but I thought you might find a lot of this stuff interesting. Anyway, so here's an example of a, I'm going to turn off the audio here, of a robot here that's been programmed to be able to catch a ball. And now this, while it's, as for humans, it might seem like a very simple task to do. A child learns this every day. There's a huge number of things that have to happen for this to work, apart from just the visual object identification and parsing and getting a working visual system going. You have to have hand-eye coordination. It's an extraordinarily complicated task. And this robot can, catch multiple balls at the same time. It does motion tracking. Think about all the processes that you've studied up to this point. Apart from things like memory, it doesn't have to have a long-term memory, but it has to have enough memory to do pattern recognition and learn from its mistakes. It has to implement attention. It has to be able to do a lot of the things that we studied. So how do you get to this point? Well, you have to understand the human brain first and understand how we process information before trying to design something like this. I'm just going to tick through these. This one you can find through Wired under the following title. This is probably the most prominent example of robotics and artificial intelligence to date. It's the Watson project. And Watson recently challenged the Jeopardy champions, and if I'm not mistaken, they won. The robots won. And here's a little brief documentary on it. I'm going to just play this verbatim.
What's the amount of science involved when Watson answers a single Jeopardy question?
Watson, what is polka? That is correct.
There's natural language processing. There's machine learning. There's knowledge representation and reasoning. There's deep analytics, and it all happens in just 3 seconds.
What is South Dakota? That is correct.
The computation that Watson's performing is what we call embarrassingly parallel, which means that lots of different threads, different computations, are triggered all at the same time.
If you tried to run Watson on a single processor, it would take a couple of hours for each question. But IBM had to create a new computing infrastructure that would allow them to do lots of parallel distributed computing to really bring down the time required to answer a question.
So we set about building an optimized system. I use the word system because it's really a combination of hardware and software.
That application is the key. Start with that. What are the key requirements for that and how they need to be satisfied? You bring the elements that are required to take care of that application need.
We ended up using one of IBM's high-performance computing platforms, one that scales very well, meaning it can run massively parallel computations. And this was the Power 7 platform. It has many, many CPUs, all densely packed together, sharing memory.
Most importantly, and one of the biggest things that separates Power 7 is bandwidth. Watson, for example, has to access terabytes and terabytes of data to answer a question. Our processor has 500 gigabytes a second of capability. Most other processors are down below 200.
The Power 7 system is tuned for very rapid, deep analytics of massively parallel problems.
Okay. So wait, let's. I think you get the idea from looking at this. But Watson is an example of what we tried to do in the '60s, called Deep Blue. We tried to design a system that could answer questions and beat humans. And Deep Blue was beating chess masters in chess tournaments. But that was a very restricted knowledge base. So Watson is now a more contemporary version of the Deep Blue project that can draw on all information, from all of our culture. It has access to all databases and can do an enormous amount of things in a very short period of time. And you notice they mentioned parallel systems. That's really important because in order for Watson to achieve what it needs to do, it has to take a problem, break it apart into little pieces, and have different parts of its brain work on those pieces in parallel at the same time. And that's really a strategy that computer scientists developed on their own, but they also learned a lot from neuroscience because that's what the brain does. It takes a problem, breaks it down, and works on it in parallel. You can also find interesting articles of that in the New York Times, has several, is another good source for a lot of artificial intelligence stuff. Let's skip here. This is another Watson one. And then you have very simple ones. Well, that's the most powerful one. There's examples of AI here, there, and everyone. There's examples of programs that can generate poetry in the style of Melville, of Dickinson. There are music programs that can write music in the style of Bach. And what that means is that really, if you give a computer a discrete set of rules to follow, it can do a very good job at following them. The more wishy-washy the rules, the more it behaves like a computer and less human-like. It starts to fail when the problems are not poorly defined, and then you can tell it's not a human when you look at it. If you remember from your reading, the ultimate test for a computer is called the Turing test, which means that if you put a person in a room and you ask them to judge communications that come into that room and ask them whether they think it's a computer or a human, the ultimate test for an artificial intelligence system is if it can fool the human. If it can have a conversation with the human and the human believes that they're actually talking to another human rather than the computer. Now, let's see, I'm going to restart this one here. We can implement artificial intelligence at a society level as well. It doesn't have to be at the level of the computer. This is a famous model of traffic flow, and traffic jams are pretty much created by human error. If you'll notice, there's a bunching going on, and that bunching gets worse and worse over time, and it was probably started by some random fluctuation in traffic. Somebody maybe tapped on their brakes for just a little while. Oops, sorry, this is slightly out of your view. And as a result, this now massive traffic jam is starting to develop just based on a simple random fluctuation. If everybody was driving the same speed, we wouldn't have traffic. And this is something where robotics can come, artificial intelligence can come into play. It can make decisions at a society level. Google is currently developing a car that drives itself. And if you have an interaction with this type of artificial intelligence and a car that is autonomous, then we might be able to get from A to B without any hassles. Think of it like an individualized subway car. Sorry, like I said, I promised you this would be in totally random order. So artificial intelligence needs to often have a vehicle if it's going to make a place in our society. And so there's a lot of parallel work being done in robotics, developing systems that can navigate through the world in a more animal or human-like fashion so that we can implement problems in the field where they need to be solved. So you have, many of them are patterned after biology. For example, this is a very canine or feline-like walking system. And the advantage of this robot is that it can traverse incredibly rough terrain that might challenge a robot with wheels. Now, you might think, well, this is an artificial intelligence, it's just a robot. But there is actually intelligence that goes into this. The person who's controlling this is basically just saying, go this way, go that way. The robot is making all these decisions on its own about correcting bad footholds. Um, it learns how to navigate through terrain. So these are examples of robots that handle subconscious processing, things that we take for granted. All have to be programmed into these robots for them to perform successfully. Um, let me give you another example of that, if I can find Big Dog. Okay, we'll come to Big Dog in a while, and that's I'm comparing that to robots like these. A lot of people, when you think of robots, a lot of people when you think of robots, you think of these robot wars that they have on television, which are quite hilarious. But these are all just machines. They're computer controlled. They don't really do any form of artificial intelligence whatsoever. Maybe a step above that is a robot that has a very discrete solution. It can do pattern matching, like this Rubik's robot that can solve Rubik's Cube puzzles. It sees a pattern, it can analyze it very quickly, and then come to a discrete solution. That's all it does. And a lot of robots in our society today, watch how fast it goes when it figures it out. It's getting all sides, and then it just decides, okay, I know the solution. A lot of robots that we implement and artificial intelligence solutions that we implement in our society today essentially solve one problem really, really well. And that's the challenge of artificial intelligence, is how do we get all of these systems, how do we get a robot that can do all of the things all robots can do in one machine, and then how can we get it to work inside a real 3-pound box the size of our skull? That's a huge challenge. You saw how big Watson was. Watson takes up an entire room. How do we make things so small? That's the marvel of the brain, right? Here's an example of training in robots. Now, in artificial intelligence systems, we don't just tell them what to do. They have to learn via trial and error. So this was a robot that was programmed with all the necessary components in order to be able to see a target and to learn how to fire an arrow. But after several trials, it eventually learns how to aim, how to shoot, and get the result it wants by successive approximations. And as you can see, this is toward the end of the training session. It can now, it will eventually learn to hit a bullseye every single time now and perform better than a human. But I just wanted to show you that this is how they work, how the learning systems go. Okay, here we go. But you can see it's hitting the target even though the arrow doesn't stick. And I have another example here with a robot that can flip pancakes. Not very well that time, though. That one's yours. Aha. So now it can flip pancakes like a champ and do it better than a human. So that gives you just an idea of how the learning systems go. Some other silly robot things. When we're talking about having a shell for the robot to navigate in, one possibility is building a bipedal robot. This is what we usually think of when we fantasize about robots in the future. And this is Asimo, which is a robot that Honda has been working on for years and years. And Asimo is incredibly human-like. It can move, it can dance. Recent versions can climb stairs and actually run. This might be an early version where he kind of walks a little funny. But imagine the applications of putting something like this in space, or in hazardous environments, human rescue, etc., and giving it a number of intelligences. Oh, now it's going to break dance for us. It's going to give it a number of intelligences where it can make decisions on its own at a low level, and we just guide. the larger decisions that need to be made. So the more AI you pack into a robot like this, the less we have to worry about controlling it in small ways, and we can just say, hey robot, go here and do this, and it will do it. The other advantage of this is we might be able to pump in everything via wireless technology, meaning that you don't have to have a computer the size of Watson. What you can do is you can have a computer the size of Watson in one room and beam it into a body like this wirelessly and control it from afar. And that would be a huge advantage, meaning we don't have to have a 3-pound brain for robots. We can have large brains in smaller bodies. This is an example of the first AI system, which was designed way back in 1936. It was designed to mimic the human voice, and all it is it's air being pushed through some filters that make it sound like, that mimic changes in your vocal cords. And so what it can do is reproduce the physical aspects of human speech.
Uses only two sounds produced electrically. One of these represents the breath. The other, the vibration of the vocal cords. There are no phonograph records or anything of that sort. Only electrical circuits, such as are used in telephone practice. Let's see how you put expression into a sentence. Say, she saw me, with no expression. Now say it in answer to these questions. Who saw you? Whom did she see? Did she see you or hear you?
So you can hear the robot, or rather the computer-assisted mechanical device, was in a sense kind of programmed to imitate human speech that way. Anyway, those are the earliest examples of robotic and popular culture. You can see this timeline under Building Smarter Machines in the New York Times. This is an example of a sort of a cyborg mechanism. A cyborg means mixing human and machine-like components together. It's a very science fiction thing to do, but right now if you think of a cochlear implant, we can insert artificial cochleas into young children who are born deaf and actually give them the ability to hear, and this is something that's very much around today, and we're fast on our way to building an artificial retina for people who have vision problems. And this is an example of a man who lost his eye and built his own robotic eye. Now, he can't see with it, but what he can do is it works like a remote camera, and he uses that eye to film things, so he can sort of film on location. Now, imagine if you combine this technology with a brain interface, you might be able to interpret those images. There are companies like Second Sight that are actually doing this, but they don't have any films because their technology is highly proprietary. But this sort of gives you an idea of what might be happening in your lifetime. Now, there's a whole other world of robotics dedicated towards studying emotion. A lot of these robots that we've talked about need to be able to understand image processing, just to be able to navigate through the world. But what about understanding human faces and features? Some computers have now been programmed as an interface so that you can talk to the computer and the computer will talk back to you, and not only will it understand your language, but it will understand the way you're saying things. And this is a really interesting line of research because now we can sort of put computers in a location in the world where we might not be able to put a human, or for example, one current application is a program that allows doctors to see more than one patient from their desk. So they can have this fake nurse sort of interview the patient before the doctor actually sees the patient and takes care of all the basic simple questions before the doctor gets to the patient, so they don't waste a lot of the doctor's time. Here is an example of a DARPA project. DARPA is the military research wing of our government, and this is how they're training up a artificial intelligence system to be able to identify objects. So this is the actual image that it's seeing. This is what the computer is interpreting after pre-processing. This is much what visual cortex sees after it's just taken a very quick view of the world without color. And then it's comparing it to feature maps that it has in its memory and determining whether it knows what it is or not. If you skip toward the end, I think it... Oh, I can't remember how you can tell if it's getting them right or not, but there is a way. How do we deploy these systems currently?
That's where we're at right now.
A lot of them have been employed in the military. So this is an example of a simpler robot, but has been very effective in the field. You can send a robot like this into a very, very dangerous situation, and it can either collect information. They're also used, or it can actually perform military functions. This is one sweeping for mines. They've been used in 9/11. They were used to perform human rescue. They could provide military features, like I said, and we even have drone planes now, planes that are flown remotely, and all of those have to have artificial intelligence systems aboard. You can see a lot of these at TED.com. TED.com has an enormous number of great talks on robots, and I'm just going to throw some names at you. Hod Lipson, building self-aware robots. Henry Markham, building an entire brain in a supercomputer. David Hansen, this is an example of a robot that's trained to mimic emotional responses. So now he's smiling, and Einstein sees him and replicates that emotion. He's replicating a frown. So this robot has to have the ability to not only identify human facial features, but be able to understand what they mean. It's hard because David has this enormous mustache, if you haven't noticed. So I'm assuming this robot has been trained on a number of different facial features, including facial hair, and does a very good job at all of them. This is an artificial intelligence pet called Pleo, and Pleo is armed with tactile sensors and multiple remote cameras, and I've actually got to play with Pleo, and this demo doesn't do it justice. When you pet Pleo, it feels like you're playing with a real cat, albeit a very calm one. It responds to your touch. When you touch it, it moves into your hand. It can see your hand and navigate towards you. Unfortunately, the one on the left decided it was going to take a nap. But this one here, I think that the thing to notice is when the demonstrator scratches underneath its chin, you can watch Pleo react to that and move in a way that's very cat-like. Yeah, he's trying to spend a lot of energy waking the other one up. Unfortunately for him, this wasn't the best demo he's ever had. But again, they're really convincing. And I think off the shelf, these are only like a couple $100, maybe $100 each. So he put $1 million worth of research into it. But yeah, see his head raised slightly. But an example of how tactile sensors can be put into the system. This is another robot called Big Dog. I told you about this one. Okay, Big Dog is pretty amazing in that it does a number of low-level functions very efficiently. It's been designed after a horse, as you can tell, and it's designed to carry an incredibly heavy payload. It's gas-powered and noisy right now, so it's not very useful yet. But Big Dog can handle incredibly difficult terrain. And what I want you to notice is when it starts to get into ice and snow, it's going to make mistakes like a human would make. But check out how quick it can do error correction. It's pretty amazing. There's a huge number of computations that have to go into effect very quickly in order to correct for this this error. It's incredibly robust. If you kick me like that, I would probably fall down. And it falls and it recovers in the same way an animal would in slippery or icy conditions. It even looks like a deer struggling to regain its balance. then robotics and artificial intelligence systems can go into uncharted territory. Dennis Hong has a talk on TED where he designs a bunch of robotic systems after nature and vice versa, but he also allows computers and robotics to design themselves to allow them to come up with the most efficient systems for walking that they can come up with. And he comes up with some pretty wacky designs. And who knows where this research is headed, but by allowing the robot to, or the artificial intelligence system to find its own solution to a particular problem, we might be able to design an entirely new method of artificial intelligence and robotics that allows us to solve very unique problems. Like that, a third leg that flips underneath its body and the whole body rotates. That wasn't something that I believe that they predicted would happen, but the robot decided that that was the best solution to do on its own. So he has about 7 different robots there that he created. Okay, that's silly. So I'm going to talk about one last thing here, and then we'll close up. We're now designing computers that are more like the human brain. The human brain is a highly dense, interactive network with very, very quick, rapid responses, go, no-go responses for neurons, with inhibition and excitation working in a neural network. And computers have done a lot of this as well, but we're actually designing new chips now that react incredibly quickly and can do a number of computations in parallel. So in your lifetime, in the next 50 years, we're going to see remarkable changes, and I believe you're going to see an entirely new fields develop. I mean, psychology will always be around because there will always be humans, but there's going to be computer psychology. You know, computers, I'm guessing, are probably going to be so sophisticated that we are going to have a whole field dedicated to studying the minds of computers, not just the technological aspects of them, but how they work and how they function and how they process information on their own. Anyway, I hope you learned some pretty fun stuff out of this, and it's been a pleasure having you all in class. I hope I get to see some of you in person in future classes, and oh, that's my alarm. And, you know, best of luck finishing up the course, and I really hope you learned something and you got something out of this that will help you in your future. Until then, take care. Bye.